The topic of this YouTube video is Water Quality and Treatments, Artificial Intelligence and Designing AI Agents for Automation, Technologies, Algorithms, Programming, and Applications. Part 1. The Problem Space and the Need for Intelligent Automation. An introduction. The urgency of water quality management in the 21st century. Water is arguably the most vital resource for life on Earth. Yet, the global water crisis is deepening. Urbanization, industrialization, agricultural expansion, and climate change have severely compromised the safety, sustainability, and availability of freshwater systems. Contaminants like heavy metals, microplastics, nitrates, pharmaceutical residues, and pathogenic organisms are increasingly common in both surface and groundwater sources. Traditional methods of monitoring and treating water have proven inadequate in addressing these dynamic, distributed, and multidimensional challenges. To meet the demands of 21st century water governance, there is an urgent need to adopt advanced technologies that not only enhance detection and treatment accuracy, but also automate responses, optimize systems in real time, and reduce human error and operational costs. This is where artificial intelligence, AI, and more specifically, AI agents designed for autonomous environmental decision-making, become critical. The multi-layered challenges in water quality and treatment. Water quality monitoring is a data-intensive, labor-intensive, and time-sensitive process. The challenges can be broadly categorized into 4 key domains. 1. Real-time detection and diagnostic. Traditional sampling and laboratory analysis can take hours to days, which is insufficient when waterborne threats may need intervention within minutes. Sensors deployed in situ often generate massive volumes of time series data, but lack the analytic frameworks to derive actionable intelligence autonomously. 2. Multi-pollutant complexity. A single water source can contain dozens of interacting contaminants, each with its own distinct detection signature and treatment pathway. Addressing them individually through rule-based systems is neither scalable nor robust. 3. Treatment process optimization. From coagulation and filtration to advanced oxidation processes, AOPs, and reverse osmosis, treatment systems involve complex chemical and mechanical interdependencies. Water composition, flow rates, energy consumption, seasonal variation, and regulatory constraints influence these. 4. Regulatory compliance and predictive risk management. Water utilities must comply with stringent regulations set by environmental agencies. However, compliance is often reactive. There is a critical need for predictive systems that anticipate threshold breaches and automatically intervene or recommend targeted actions. AI in water systems, the new paradigm. Artificial intelligence, spanning machine learning, deep learning, reinforcement learning, and symbolic reasoning, offers a paradigm shift. AI can learn from data, adapt to novel scenarios, infer hidden patterns, and optimize complex, nonlinear systems under uncertainty. In water quality and treatment, AI can be used not only for predictive modeling but for automating control decisions and optimizing resource allocation. For instance, anomaly detection algorithms can continuously scan sensor outputs to flag abnormal pollutant levels. Neural networks trained on historical treatment outcomes can dynamically adjust dosing parameters to optimize treatment outcomes. Deep reinforcement learning agents can operate as digital twins of entire treatment plants, learning to minimize costs while maintaining compliance. Designing AI agents for water automation. In this context, an AI agent is an autonomous software system capable of perceiving its environment via sensors, reasoning about it via data models, and acting upon it via system actuators or recommendations. A well-designed AI agent for water treatment must integrate several components. Perception module interfaces with IoT sensors and telemetry systems to collect real-time physiochemical parameters such as pH, turbidity, dissolved oxygen, and chemical oxygen demand (COD). Knowledge representation and contextual modeling incorporates ontologies of pollutants, treatment techniques, and regulatory thresholds to support semantic reasoning. Decision engine employs machine learning classifiers, optimization solvers, or reinforcement learning policies to select appropriate actions based on state observations. Learning engine continuously improves the agent's performance by learning from outcomes, either in supervised mode, with human-labeled feedback, or via unsupervised data clustering and trend analysis. Communication interface allows interaction with human operators, cloud systems, and other AI agents in a distributed network. These agents can be embedded within smart controllers, cloud-based SCADA systems, or even mobile field devices, depending on the operational architecture. Technology stack, from edge to cloud. The technological backbone of such AI systems is a layered integration of hardware and software components. These include edge computing devices. Low-latency processors at sensor nodes enable preliminary data processing and real-time anomaly flagging before data is transmitted to central systems. Cloud infrastructure provides scalable data storage, model training environments, and multi-agent orchestration platforms. Machine learning frameworks, TensorFlow, PyTorch, and scikit-learn power model development, while tools like Apache Kafka or MQTT ensure robust data streaming. Interoperability standards, open data protocols, e.g., OGC SensorThings API, and semantic web technologies, e.g., RDF, AL, ensure AI agents can integrate across water utilities. Algorithmic innovations in water treatment AI. The success of AI agents hinges on the selection and engineering of suitable algorithms tailored for water systems. Some key approaches include time series forecasting. LSTM networks and transformer-based models can predict pollutant concentration levels hours or days in advance, supporting preemptive actions. Anomaly detection. Isolation forests, autoencoders, and one-class SVMs are effective in flagging rare contamination events with minimal false positives. Control optimization. Deep Q learning and policy gradient methods can learn complex control strategies for dynamic dosing, pump scheduling, or membrane cleaning. Hybrid models, physics-informed neural networks, PINNs, integrate domain knowledge from fluid dynamics with data-driven learning, improving generalizability and interpretability. Towards an autonomous water future. The convergence of AI, sensor technologies, and digital infrastructure heralds a transformative moment for water quality and treatment. AI agents can act as autonomous environmental guardians, detecting, diagnosing, and responding to water threats faster and more precisely than any traditional method. But to realize this vision, a systemic effort is required to design, deploy, and regulate these technologies across the entire water ecosystem. The next phase of this video will dive into the practical architecture, programming paradigms, and implementation strategies for building such AI agents. It will examine how software engineers, water scientists, and policymakers can collaboratively engineer intelligent automation in one of the most vital domains for humanity's future. Part 2. AI architecture, programming techniques, and real-world applications for water quality automation. Building intelligent architectures for water quality automation. A sophisticated multi-tiered architecture underpins the design of intelligent systems for water quality monitoring and treatment. This architecture is not monolithic, but modular and adaptive, supporting decentralized operations while enabling centralized intelligence when necessary. At the most fundamental level, the architecture comprises data acquisition layer, a mesh of sensors, optical, electrochemical, spectrophotometric, deployed in both stationary and mobile units, such as drones and autonomous boats, transmitting readings like pH, conductivity, nitrates, heavy metals, and biological contaminants. Edge processing layer, microcontrollers and embedded AI processors, e.g., NVIDIA Jetson Nano, Coral TPU, perform initial analytics such as noise filtering, feature extraction, and threshold-based alerts. This layer reduces latency and bandwidth consumption while ensuring immediate responsiveness to local anomalies. Data integration and semantic modeling layer. Heterogeneous sensor data is aggregated, harmonized, and mapped to domain ontologies, e.g., Suite, WQO, to facilitate inferencing. Semantic triples describe not just raw data but its contextual significance. Ammonia detected in downstream node after rainfall greater than 20 mm. AI agent layer, the decision-making core. Here reside autonomous software agents endowed with perception, reasoning, planning, and learning capabilities. These agents are implemented using software agents frameworks, e.g., JADE, SPADE, and are often containerized for scalable deployment. Control and actuation layer. AI decisions are translated into operational changes, such as modifying UV intensity, activating chemical dosing units, opening valves, or alerting maintenance personnel. Integration with SCADA systems enables real-time supervisory control. Visualization and human-in-the-loop layer. Dashboards built with platforms such as Grafana or custom WebGL-based interfaces offer explainable AI insights, enabling transparency and override functionality for water operators and regulatory inspectors. Programming paradigms and implementation strategies. The implementation of AI agents for water treatment calls for a robust combination of programming paradigms, algorithm engineering, and systems integration. A typical AI agent is constructed as a software entity using Python, Java, or C++, and adheres to a modular design pattern, such as the Belief Desire Intention, BDI, or the Sense Think Act cycle. 1. Agent behavior modeling. Agent behaviors are coded as event-driven functions responding to environmental stimuli. Reinforcement learning policies can be embedded as callable models using ONNX runtime for low-latency inference. 2. State representation and knowledge graph. The agent maintains a dynamic belief state encoded in a time-indexed knowledge graph. This representation supports symbolic reasoning, causal inference, and multi-agent coordination. 3. Communication protocols. AI agents interact via lightweight protocols such as MQTT or COAP. In multi-agent systems, the FIPAACL communication language enables negotiation, bidding, and task delegation between distributed agents. 4. Machine learning pipeline. Data ingestion and model training pipelines are constructed using tools like Apache Airflow and MLflow. Training is conducted on cloud platforms, e.g., AWS SageMaker, Azure ML, using water quality specific datasets and is continuously validated using k-fold cross-validation and domain-specific loss functions. 5. Simulation environment. Before deployment, agents are tested in digital twin environments that replicate hydraulic and chemical dynamics. EPANET, coupled with OpenAI GIM wrappers, allows for reinforcement learning experiments with water distribution networks. 6. Security and reliability engineering. Given the critical nature of water systems, AI agents are designed with fail-safe routines, redundancy checks, adversarial input detection, and cybersecurity hardening through TLS encryption, role-based access control, and audit logs. Real-world case studies and applications. Numerous pioneering applications across the globe illustrate the power of AI-driven water automation. Smart sewage management in Singapore. PUB, Singapore's national water agency, employs AI agents for real-time wastewater monitoring. Predictive analytics identify toxic discharges and automate diversion before treatment plants are overwhelmed, reducing overflow incidents by over 60%. AI-powered remote sensing in the Murray-Darling Basin, Australia. Using satellite imagery, drone-mounted hyperspectral cameras, and AI image classifiers, agents detect algal blooms and salinity intrusions with 94% accuracy. These findings inform irrigation planning and emergency response. Autonomous treatment control in the Netherlands. At the De Dommel Water Authority, reinforcement learning agents control membrane bioreactors, dynamically adjusting aeration levels and sludge retention time. This has led to a 15% reduction in energy use without compromising effluent quality. Potable water assurance in Indian smart cities. AI systems process continuous sensor feeds from water kiosks and pipeline networks, detecting bacteriological threats and automatically initiating chlorination sequences. Alerts are escalated through multilingual mobile platforms to reach vulnerable communities. Challenges and future direction. Despite the promise, several critical challenges remain. Data quality and model bias. Sensor drift, data sparsity, and sampling errors can bias AI models. Future work should focus on developing self-calibrating agents and employing Bayesian inference techniques to quantify uncertainty. Explainability and trust. AI recommendations in water systems must be auditable. Techniques such as Shapley additive explanations, and counterfactual analysis are being integrated to elucidate model decisions. Interoperability and legacy systems. Many water utilities operate with outdated infrastructure. Middleware solutions and digital retrofitting are essential for enabling AI agent compatibility without a full system overhaul. Scalability and edge deployment. Federated learning and model distillation offer pathways to deploy AI at scale across geographically distributed sites with intermittent connectivity. Policy and ethics. Autonomous agents must operate within regulatory frameworks. There is a need for internationally harmonized standards governing algorithmic accountability, environmental impact, and citizen privacy. Conclusion: engineering a new era of water intelligence. The application of AI agents in water quality and treatment systems represents more than just a technical advancement. It is a fundamental rethinking of how we steward our most essential resource. These agents offer not only precision and efficiency, but also resilience, adaptability, and foresight. In a world increasingly defined by climate volatility, population growth, and ecological degradation, intelligent automation of water systems is no longer a luxury, it is an imperative. As engineers, researchers, and policymakers, our task is to design systems that are not only intelligent, but responsible and inclusive. With the right technological frameworks, governance structures, and collaborative ethos, AI agents can help realize a future where clean water is universally accessible, sustainably managed, and digitally safeguarded.